Okay, we are recording now. So hello to everyone who is watching remotely, and we will move on to do a variant of induction, which is called strong induction. Okay, let me get a better pointer. All right. Okay, so let's recall what kind of thing can be proven by an induction. Here is an example. You have a sequence defined using a recursive definition. This is called recurrence relation. Like so, the first element of the sequence, we start from index 0. This is, by the way, arbitrary, although conventional. So the 0th element is just declared to be -2. That's called the base case of a recurrence relation. And then there's a recursive part of the definition. And that part says that for any index from 1 on, the nth element of the sequence is defined in terms of n-1st element of the same sequence by taking that one, multiplying by 5, and also adding 8 times n, where the n is this index. Okay, so this defines an infinite sequence, right? Because it's like a recursive code. And here is a theorem about it, that for any n, this h-nth element has a closed form formula, which is 1/2 times 5 to the nth power, and then an offset -2n minus 2.5. So if you look at this recurrence relation, this is maybe somewhat intuitive. You start at some point and then you multiply it by 5. And then you add some sort of offset, but you multiply by 5 every time. So maybe it's intuitive that it's like an exponential series. Like the next guy is 5 times the previous, and the previous is 5 times the one before that. So perhaps it's not so surprising to find this term, but somehow the effect of adding this shift and starting from -2 somehow translates into the closed form formula, first of all, growing somehow twice slower than just powers of 5, and also having this offset. So we'll talk later about how to find these formulas, but let's see, okay, this is something we can prove by induction, right? How would we do so? Separately for the base case and separately for the recursive case. For the base case, this will be the base case of the proof. For n equals 0, we prove that this formula evaluates this base case declaration of what h0 is correctly. So let's test. If I plug an n equals 0 to this, here I get a 1, so it's 1/2. Here I get -2, and sorry. For n equals 0, here I get the 1, so it's right. But here I get the 0, so this part vanishes, and now I have a -2.5, and this minus that is indeed -2. Okay, so the base case checks out. Okay, what about the recursive step? So here it is again, the recursive definition of the sequence and a claim. And now let's do a little voting. Which of these four variants describes what should be done in the inductive step of the proof. So once you're done with the base case, so you do show that this is true for n equals 0. Okay, it's the easy part. Then what remains to be proven in the inductive step? It is some implication, but exactly which of these four is the one you should be proving? Okay, I see a bunch of B's, and that's correct. But keep on also looking for alternatives. So B is correct because is a correct answer, because this shows that if the formula is correct at point K, then it's correct at point K plus 1. So the predicate we're proving is that the formula here, the closed formula, is correct about this sequence. So here that if it's correct at point K, then it's correct at point K plus 1. And we want to prove it for all K starting from 0, because then the base case and the inductive case are going to be connected, right? If we, for example, prove this only starting from K equal 1, then this would not connect to the base case, because in the base case, we only showed that this is true about n equals 0. So we couldn't instantiate the assumption if we only showed this implication for K starting from 1. Unless we added the case of n equal 1 to the base case, right? We could say, hey, for no reason really, but let's just add H1 that it's correct into the base case. Okay, you could, it's not needed, but you could. It would be necessary if for some reason you only proved this implication for K greater or equal to 1. Okay, since nobody is saying so, let me just point out that this is also correct. So what this implication says is that starting from index K1, if formula is correct at point K minus 1, then it is correct about point K. And this is basically just change of variable, right? So K here becomes effectively K minus 1 over here. And that's why if we started from 0 here, we have to start from 1. So that K minus 1 is 0, right? There is no, it's not set in stone. Like, do you want to prove this one? Go ahead. Do you want to prove this one? Go ahead. You're proving the same implication, really. You're just using a different notation for it. So you chose to index the hypothesis and the goal using a pair K minus 1K, rather than index the same hypothesis and the goal using pair K plus 1. It's completely up to you, right? Just like the choice of the variable, like, you can call it I or you can call it N. It does not matter. Okay, so why do these things, is a comfortable things to prove by induction? Let's have a look how this proof would go. So what we are proving in this step is that frame over there, the option B, which is just repeated here. And here is the sequence defined and the claim about it repeated, right? So we want to prove the purple-blue equation given the green-red equation. So we're searching for something here that relates, something in the goal that relates to the hypothesis. And the easiest relation is between the purple term and the green term, because that is exactly how HKs are defined to begin with, right? So by recurrence relation, you know that this term is 5 times this guy plus 8 times, and now you have to be careful. You instantiated this formula with n equal K plus 1. So therefore, n minus 1 here became K, but n here must stay K plus 1, right? Because, the choice of these indexes and the choice of these indices here are going to make some of these movements potentially tricky, right? You just have to watch out for this. it's you might want to adjust what you're proving so that it's convenient, the notation is convenient, but that's not guaranteed to work. It might be convenient in one step and a kind of less convenient in another, right? Okay, so just be careful when doing these instantiations and be mindful of the fact that these are variables which are shifted around, right? So this n minus 1, and you have to sort of do the corresponding one, regardless of what your instance, however you instantiate this n with, right? Here you instantiate with k plus 1. Okay, so now that you got this, boom, you can use the inductive hypothesis, right? Replace the green guy with the red expression, because that's what inductive hypothesis gave you. And after that, it's arithmetics, and just do this, and let's hope that this does become the blue expression, or if it's not, there's something, there is some mistake you're making. And let's not focus on this exact algebra here. You can scrutinize it or right now, or download lectures from the site. But algebra does work out. Okay, so okay, good. Now, so let's see if this can be used for every. So okay, we introduce recurrence relations, and you can see that induction is like a perfectly attuned tool to showing closed formulas for a given recurrence relation. But you might have noted that in the last problem on the homework, where there was this little code called mystery, and it actually used a call to mystery, created two calls to mystery again, but using reduced parameters. That created the recurrence relation, but it's a recurrence relation that had two calls rather than just one in here. And you can argue this by induction, so that kind of stretching how you think about induction. But we'll see in a second a cleaner way. I mean, not a cleaner, both are clean. It's just a sort of a more general way to approach this. Take, for example, a Fibonacci sequence. It's also a recurrence relation, right? First terms are 1, 1, and the next term is defined as the sum of the previous two. Okay, so let's have some theorem about it. Namely, that the Fibonacci sequence grows less than exponential base 2. Okay, this is maybe intuitive, because if you just took the previous one twice, you would get an exponential series. But here you don't do the previous one twice, you take the previous and the one before. And if you remember how Fibonacci growth, the one before is smaller than the previous one. So it grows smaller than an exponential. Okay, it's a reasonable hypothesis. And so you just write down a bunch of first elements of a Fibonacci sequence, and it will be true. Okay. Okay. So base case. So I guess, let's start at some place, right? We're asked to prove it from beginning from 0, index 0. And it is true, because 2 to the 0 is a 1, and this guy is a 1. So this inequality holds. I mean, this less than holds because 1 is equal to 1. So in particular, it's also less or equal. Now, if in the inductive step we try to follow the previous blueprint, and we say, okay, let this be the goal of the inductive step, that at any index starting from the 0, about which we prove, by hand, that the formula, that the predicate holds, if the predicate holds for that index, then it must hold for the next one. Okay. Standard way. But that, however, doesn't fit, because in this first step, this one of this inductive proof, I will try to, my goal is to somehow upper bound fk by 2 to the fk plus 1 by 2 to the k plus 1. So I'm rewriting fk in terms of the previous elements, and I'm hoping that I can use the inductive hypothesis to these previous elements, and the rest will fall true. And now, if I do this, then in this first step, I'm going to rewrite fk plus 1 using this formula. Now instantiated for n k plus 1, so this guy becomes fk, and this guy becomes fk minus 1. But here already I have issues, because I'm trying to prove this implication for k starting from 0. This expression doesn't even make sense for k equals 0, because it seems to refer to some object which is like a minus first element in the sequence. But the sequence started at index 0, so there is no such object. Well, let's try to fix it by this, okay? Let's just add one more element to the base case. So let's grow the base case base. And sure, we can do this. So let's just prove by hand that this bound holds about index n equal 1. Okay, so this is 2 to the 1, which is 2. And this guy is a 1, so the inequality holds. Good. Let's now try to use the inductive step now that we have both of these guys here. So good. So in other words, we'll move the bar, and instead of trying to prove this implication beginning from k equals 0, we'll try to prove this implication starting from k equal 1, right? Because, yes, so good. So we're rewriting k plus first element as the sum as before. And now, good, both of these are defined because k is greater or equal to 1. So this is index at least 1, and this is index at least 0. So far, so good. Both of these are defined. But based on this inductive hypothesis, we can only assume that this guy is upper bounded by 2 to the k. But what about this one? Okay, it doesn't, this assumption, this inductive hypothesis says nothing about, is there some upper bound about this object? Now, you should be like, well, but didn't I use induction to, somehow the previous step of the induction, I have proven then this object also is bound by this bound, right? Exactly. But this step cannot have this form. You basically must amend this implication to be assuming the predicate holds about fk and assuming that the predicate holds about fk minus 1. Perhaps under these two assumptions, I can now prove this bound, but I cannot prove it based on this one alone. Okay. So in my suggestion for how to do homework, it was exactly like this case. And I said, okay, think about the predicate that says that this formula is true about two consecutive elements. Think of that as your predicate. Think that the predicate you're proving is that this holds about not just n, but also n plus 1. In other words, that both fn is upper bounded by 2 to the n, and also fn plus 1 is upper bounded by 2 to the n plus 1. Now the standard induction will work, because your predicate applied to k minus 1 would show that both of these are bounded respectively this by 2 to the k minus 1 and this by 2 to the k. And now under that assumption, you can prove that this pairwise, the bound that applies to pair holds about the next pair. What is the next pair? Fk and Fk plus 1. About Fk, we don't really need to prove anything because that was what we assumed. So the only thing we need to prove is that this guy is bound as well, right? And now you have rescued standard induction, and it can be applied here, but let's generalize it. And that would be the strong induction. So in general, the strong inductive step would have this following general form. Okay, still general, but I will just use it with an example of this particular sequence and this particular claim. Okay, so I extend my base case. I will have two. I will have two statements of this form directly added to the base case for n equals 0 and for n equal 1. And then the inductive step will be like this. For any index after that, so starting from k1, if the predicate I'm proving holds about not only case at case index, but about all indices before that. So starting from index 0 and everything in between. In the previous form, I only assumed this part. Now I'm going to assume all. Under such strengthened, modified inductive hypotheses, I will now prove that the predicate holds about the next index, k plus 1. Okay, so it's this part that is modified in the case of strong induction. Okay, let's postpone actually proving this. Okay, that this works for this case, for this recursive formula and this claim about it. But what is it in general? Okay, so I have some predicate which I'm proving directly about two different indices in the base case, and then I'm having this in this inductive step. I want to prove that if the predicate holds about all indices up to k, then it holds about index k plus 1. This is the general form of strong induction. Let P be this predicate parameterized by some index n. And in the previous slide, this is the case for t equal 2. But it doesn't have to be t equal 2. You just have some number of indexes thrown into the base case and proven directly. So the base case says somehow must prove that the formula holds about index 1, holds about index 2, and holds all the way to index some threshold index t. And then for any index after that, we prove this. The implication has this form, strongly inductive form. If the predicate holds not just about index k, but about all previous one as well, then it holds about index k plus 1. If I prove these two things, then it will also follow that the predicate holds for all indices, just like in the case of standard induction, right? Again, what was the difference for standard induction? The base case, all of these were out. They were not here. And the form of this implication didn't have any of these elements. It only had this one. Okay. Even this is not the most general because it's like we're proving stuff starting from index 1, right? You've seen examples where like maybe you want to start at index 0. So the beginnings of these sequences would change to 0, right? In that case. But let's also see what does this implication mean. You can restate it like this. For any k, at least t, if the formula holds for all indices in this range from 1 to k, then it holds about index k plus 1. Okay, this statement is the same as this one. Okay. Now, why is a strong induction work? So let me say, okay, does strong induction contradict regular induction in somehow? How are these two compared? How come they both exist? So you can prove these statements in two different ways. Well, the second part shouldn't surprise you. There's many proofs of the same correct thing, right? So perhaps the same thing can be proven by standard induction. Perhaps the same thing can be proven by strong induction. Perhaps that thing can be proven directly in using some other argument still. So there is no contradiction there. Also, if you do this trick that I told you before, which is you create a new predicate, call it P prime, which says the P prime about some index, that says that the predicate P holds not only about this index, but about all indices at that from the beginning to that index. You see, this statement is also can be cast as some predicate on K. Let's call it P prime of K. At that point, this induction it can be stated as a standard induction. Assuming P prime of K, I'm going to show you P prime of K plus 1. Now, if you look at P prime of K plus 1, what does it say? It says that P holds for all indexes up to K plus 1. Now, since you're assuming that P holds for all indexes up to K, that part is immediate. The only part that's missing is whether it holds also about K plus 1. So when you're proving P prime K plus 1, you're really proving Pk plus 1, because all of these were already part of your assumption. So strong induction is really nothing new. You can recast it as standard induction by just a sort of a generalized, if you will, predicate that says that some underlying predicate holds not just about one point, but the whole range of points. So in that sense, there's no contradiction, because they're one and the same thing, just squinting your eyes differently. Is proving something by strong induction harder than proving by standard induction? No, except that if you get lost in notation. But as long as you don't get lost in notation, which indeed is that happens to the best of us, and only practice can improve your comfort with the stuff, is that it's in this step, using in a strong induction proof, you assume more, but you still have to prove the same thing compared to standard induction. Assuming more in a proof can only be more helpful to you. Having more assumption, it's like as if your inductive hypotheses just got multiplied. So you can, if you need something, you can now use it. It's as if somebody offered you on a plate extra stuff that you can use in your proof. You didn't have it before, you couldn't use it, now you can. So the proof can only become easier. Okay. minus notation stuff. Okay, so let's say we have some predicate we want to prove starting from index 4. And let's say that we have proven by base case that it holds about 4 and 5 and 6 and 7. If we want to show by strong induction that it holds for all indices after that as well, what do we have to prove? Which of these would prove it? I mean, this part would prove it, right? If we proved this, it would imply the theorem, but it wouldn't be a case of the strong induction proof. It will be the standard induction proof, right? This one would also prove it, by the way. If we proved this, right, the theorem would be true. It turns out that we don't really need these points in the base case. This would suffice because this part together with only this already improves this black theorem. But again, it wouldn't use these base cases and it would be a standard induction. So let's look these two, right? If you, this is the one that you need, this is the one that it's the potentially easiest. In other words, you assume more and you're only proving it from k starting from 7. If you proved this, by the way, that it would the proof would follow as well, right? Because statement B implies statement D. It's the same statement, except that this one holds for all k starting from 4, and therefore, in particular, it will start from. It will also hold for all k starting from 7. Yes. So each A, B, C, D, all of them would, if you proved it, it would imply this theorem. But this is the one that you should be doing because out of all these three, this one can only be easiest to argue. In particular, this one is implied by all these, but not vice versa, right? So this doesn't imply this, right? It only shows for k starting from 7. Who knows whether this implication holds for k equal 4, 5, and 6? Okay. Okay. You know what? Let me skip more. And this is the same stuff, but now written in a slightly different way, not as a big conjunction, but as a statement that says the predicate holds for every index in this range. Right? It's the same as on the previous slide, but now just restated as so. Okay. So let us. This is a. I still didn't show you the proof that strong induction actually works for. Didn't show you that the strong induction actually works for Fibonacci sequence. So F0 is 1, F1 is 1, Fn is Fn minus 1 plus Fn minus 2, right? The Fibonacci sequence, and we have a claim that for every n, Fn is upper bounded by 2 to the n. Okay, so because okay, let's prove this for base cases. Base cases would be n equals 0 and n equal 1. Okay, so F0 is 0, and this is indeed upper bounded by 2 to the 0, which is 1. Sorry, F1 is 1, and it is upper bounded by itself. Okay, and 1 is 1, which is upper bounded by 2 to the 1, which is 2. Okay, believe me that you need both of these into the base case, and let's see why in a second. So inductive step, but this is by strong induction. So what is the form of the statement we need to prove? That for every k starting from 1, okay, but again, choice of index is arbitrary. That's how I'm going to do it. If the theorem holds, if it is true that for all j from 0 to k, it was true that fj was upper bounded by 2 to the j. So if all this holds, then I want this theorem to be true about the next index, which is k plus 1. So that fk plus 1 is upper bounded by 2 to the k plus 1. Okay, so this is my strong inductive hypothesis. Okay, it has this new form of the predicate holding not just about one spot, but about the whole range. Okay, so let's prove it, and this will be, what can we do? As usual, this part of the claim is a recursively defined object. It's defined in terms of previous ones. So let's try to do this. N is k plus 1. So this is fk. This is fk minus 1. Okay, let's first test that these things are well defined. K is at least 1. So this is at first at least k. 1, this is at least 0. We are good. In both cases, these are well defined. Okay, now can we use the inductive hypothesis to upper bound this guy by 2 to the k? Well, yes, because so let's do it slowly. So here we used the inductive hypothesis with j equal k, and j equal k, sort of rather obviously, is in this bound, is in this range. Okay, let's try to now, can we upper bound this guy by 2 to the k minus 1, right? So okay, it's here that I used this inductive hypothesis, right? Can I upper bound this guy by 2 to the k minus 1? Well, can I use the inductive hypothesis with j equal k minus 1? Okay, when can this go wrong? Well, we have to ask, is k minus 1 in this range? So it will always be, except of one case, except if k is equal to 0, right? For any other, k minus 1 is clearly in this range, right? So, can k equal 0? No. And that's why I need both of these into the base case, right? Because otherwise I couldn't start this. I need both previous guys to fit into the range that I assume in the inductive hypothesis. I need both index k and index k minus 1 to be in here. So this thing at the minimum must include 2 objects. So this induction is going to start working if I have to hook it up somehow, right? It assumes something about two consecutive elements. So it cannot be started unless 2 consecutive elements were put into the base case and shown directly, or otherwise this would be an empty statement. So what did I prove? That if I have some thing holds for 2 consecutive ones, then it holds about the next one. If I don't have some 2 consecutive ones to hook it up at and get this going. So here in this, right, I use this inductive hypothesis with j equal k minus 1, and it was crucial that k is at least 1, or otherwise this index would not be in this range. And now I'm practically done, because the rest is simple algebra, right? So the rest is just to show that this is at least, it's smaller, it's no more than this, but that is, not a, you can show it, right? So for example, this is definitely less than that, because this is half that. Okay, and this is equal to 2 times 2 to the k, which is 2k plus 1, right? And if you're still rusty about exponentiations, the fact that b to the x times b to the y is b to the x plus y, or the fact that b to the x times c is same as b times x times c, etc., then it's a high time to do exercises from this chapter in the textbook. Okay, so that's why this proof becomes easy if you have strong induction, right? I'm just walking over this slowly to attune you to why I need 2 base cases, what can go wrong if you don't set this boundary correctly. Do you have questions on this? Okay. So let me. Okay, this is not what I truly wanted. Okay. Okay, let's show something else using induction. So strong induction. So I have the following problem. I want to show that using 3-cent stamps and 7-cent stamps. Suppose that post office created only 3-cent stamps and 7-cent stamps. And I want to show that you can combine these to express any integer, as long as the integer is 12 or more. Okay. So let the predicate P of n be that n cents can be expressed as some multiple of 3 and 7-cent stamps. So why is this predicate doesn't hold about 17? Yes, it does. I take 2 7-cent stamps and 1 3-7 stamps, and I get 17. Does it happen true about 11? No, because I cannot express this as a multiple of 3. I mean, directly. So I have to use a 7-cent stamp. But if I do use a 7-cent stamp, then the rest is 4, and it's clearly not expressible by either 7 or 3-cent stamp. But somehow from 12 on, it does work. So again, this is the theorem. The theorem can be stated faster as following. N can be expressed as a multiple of 3 plus 7. So n is 3i plus 7j for some ij integers. Let's test that this is true about a bunch of initial values, okay? Because we're trying to prove this predicate for n at least 12. So for 12, we already shown that this is, no, for 12, we have it. So it's just 4 times 3, right? Now, what about 13? Well, we have 1 7-cent stamp. We subtract, that's a 6, and we can express it as a multiple of 3. 14, of course, just multiple of 7, right? This suffices to prove the rest using induction. So I will argue that from index 14 on, if any integer j from 12 to, so at index k, I want to start using induction. So in other words, if the predicate holds from the first index, which is 12, up to kth, and what is the predicate? So in other words, if the predicate holds for any j in this range, and what's the predicate? The predicate is that j can be expressed using your stubs, which in this case was 3-cent stubs and 7-cent stubs. Then we'll show under this assumption that the predicate holds about k plus 1. In other words, the k plus 1 can be expressed as a bunch of 3s and a bunch of 7s. So in other words, this is the formula, that this is the implication you're proving in the inductive step. For any index at least 14, because that's where the base case stopped. We showed it for 12, 13, and 14. Why we stopped, that we'll explain later. It's not immediate yet. But we stopped at 14. So therefore, the implication we have to prove has this form. Assuming the predicate holds about any integer in the range starting from the first one, 12, and ending at k, then it also holds about k plus 1. Let's see that this is actually easy to show. Well, okay, so we want to argue that that the predicate holds about k plus 1. In other words, that k plus 1 can be expressed as a bunch of 3s and a bunch of 7s, assuming that each of these integers could be expressed as a bunch of 3s and a bunch of 7s. So here is an easy move. How can you use the fact that all of these integers are expressible as a bunch of 3s and a bunch of 7s in order to show that the k plus 1 is expressible as a bunch of 3s and a bunch of 7s? Well, how about take away 1 3 from here? If k minus 2 was expressible as a bunch of 3s and a bunch of 7s, then so would k plus 1, because k plus 1 is 3 plus this. So if this can be expressed as a bunch of 3s and a bunch of 7s, so can that, because I just take my bunch of 3s and a bunch of 7s and add one more 3. And I now expressed k plus 1 using a bunch of 3s and a bunch of 7s. But for this, it is crucial that 3 removed from my goal is within this range. So that k minus 2 is at least 12. And that works only if k is at least 14. Otherwise, k minus 2 would be outside of this bound. Yes, would be somewhere here, to the left of 12. So that's an explanation why we need to start at 14. So, okay, so if k minus 2 is at least 12, then therefore k minus 2 falls in that range. It's clearly smaller than k, but also at least 12. And so by the inductive hypothesis, it's the predicate is true. So k minus 2 is expressible as a bunch of 3s and a bunch of 7s. So therefore, if you add one more 3-cent stamp to these, then you get k plus 1. And therefore, k plus 1 is expressible as a bunch of 3s and a bunch of 7s with one more 3. And therefore, it is still a bunch of 3s and a bunch of 7s. Okay. the crucial, so this part is sort of easy, I would say, right? Like that, hey, you want to argue that some number can be expressible as a bunch of 3s and 7s if a number less than by 3 is a bunch of 3s and 7s, then add one more 3 and you get your target number. But for that to work, this range has to include k minus 2, and for that to work, this range has to start from k. This range has to go from 12 to k, where k is at least 14, or otherwise this part would not work, right? And that is why we needed 3 elements in the base case, okay? Because if we try to argue this about 14, now, if k plus 1 was 14, then of course it wouldn't work, because you remove 3 from 14 and you get to 11, and in fact it's false. 11 cannot be expressed as a bunch of 3s and 7s. So this argument that if k minus 2 is expressible in this way, then so is k plus 1, well, it's true, but it's useless. Because if k plus 1 is 14, well, it's not true about 11, so you cannot use those. So this implication is fine, but it's not useful. Okay. So now, in order to tell, like, how many base cases do you need for a proof like this, let's sort of focus, harp on this a little more. So I'm proving some predicate that holds about, starting from some threshold point, okay, 12 in this case. I'm showing that it holds about a bunch of first elements, 12, 13, and 14. And then I'm using this strong induction that if the predicate holds about all points, like this is a typo. Well, yes, it is a typo. It's a typo that doesn't really change anything, but it is a typo. I should just start from 12 here. That this implies pk plus 1. Then I'm done with the proof, right? Now, what did I really show? Sorry, I'm not going to change it online, but just imagine that there's a 12 here. What we showed is that we showed not just for k at least 14, we actually showed that for any k, if k minus 2 is expressible as a bunch of 3s and 7s, then so is k plus 1. So we were supposed to prove this, but we only proven that. Is that okay? Yes, because this implies this. Well, first of all, anything that is shown for any k clearly also implies that that something is true about k starting at 14. Good. And now, if we happen to prove a sort of simpler statement, assuming this thing already implies pk plus 1, then that also implies this thing. Because here, you're assuming this thing in particular and more. And you are asked to say, okay, is it true that assuming this and some extra stuff, pk plus 1 is implied? And yes, it is. If you showed that pk minus 2 by itself implies pk plus 1, then surely pk minus 1 and a bunch of extra stuff also implies pk plus 1. It doesn't have to be, it's not a new argument. This thing implies that. Okay, so that will often be the case. Your strong inductive hypothesis will include a lot of stuff. Perhaps you don't use all of them to show your goal. That's okay. Here you have a case. You only use that one of these predicates is true about some particular index, namely this one. That suffices. in some sense, the Fibonacci proof is also the case of this. We needed not the whole thing, but just that the predicate holds about k and k minus 1. Okay, so this will often be the case, and it shouldn't trouble you. What if we only shown this into the base case? I mean, we already talked about it. Then we will have to start this from 13. K minus 2 at that point could have been 11 for the first index, and P of 11 is not true, right? Okay. Let's try to do this for the new denominations. So if you try to use the same technique, right, but you have just some other denominations, 5 cents and 7 cents. It happens to be that these also suffice, but they only suffice for integers starting from 24. Some integers earlier are clearly multiples of 5 or multiples of 7, but not all, or combinations of multiples of 5 and 7, but not all of them, right? And in particular, 23 cannot be expressed in this way, but 24 can, and after that, everything can. Now, if you use the same, the same blueprint in this proof, then what would you do? You would prove a bunch of first cases, right? That 24 can be 25, maybe 26, okay, up to some point. And then after that point, you would be arguing what? That the next guy can be expressible as a bunch of 5s and 7s because something else was, right? But what that something else would be? Well, the shortest jump would be take away 5. That moves you from some target value, call it k plus 1. K plus 2, k plus 1 minus 5, right? Which is, okay, well, it moves you 5.5 steps back. So for that to work, in the range of in the inductive hypothesis, if you're proving about some new point, and you have a bunch of cases you can assume in the inductive hypothesis, then what you need is for this point minus 5 to be still in this range. So let's say that you prove only these points by hand. So now your inductive step has to work for 27, but it will not, because 27 minus 5 is 22. And the 22, well, I don't know if it's true for 22, but it's not in this set of cases for which you proved this thing by hand. It's not part of your base case. Here it will not also not work, right? The 28 minus 5 is 23, and it's not part of here. But here it would. So 29 would, if you right, because if you want to argue it about some point in the future, then that point minus 5 better be in the range and tested for whether it would imply the 29. 29 minus 5 is 24, so it's part of your base case, and that's the beginning. So you need all these 5 in the base case. Okay, I have a slide on the website where I'm going over this proof of this theorem, right? Like it's a direct general, it's exactly the same as the 3 cents one. I'm proving this directly, and then the inductive step is almost the same. The only difference is that I'm removing 5 cents rather than 3 cents from the target value. But that makes no difference in some sense, right? Anyway, the slide with the write-up is on the syllabus. Okay, so let me do something different instead. Here's a nice chocolate bar theorem. So let's say that a chocolate bar is rectangular. So it is always yes, like some x dimension and a y dimension, integer in both, right? And it's say m by n bars. So you have m times n little bars, and in a chocolate bar. And now what you want is to split it completely. So to give everyone the unit, okay, and you can split it along either vertical or horizontal line. And by taking the piece of chocolate and sort of breaking it along these dimensions. And let's call that action a break. How many of breaks do you need in order to completely divide a chocolate bar? Okay, but assuming that the total area is n. So perhaps it's square root of n times square root of n, or perhaps it's 2 square root of n by square root of n over 2. But it's only the area that you know. I'm going to call the number of breaks that are needed b of n. And first of all, you can be like, well, is it not dependent on the exact geometry of this chocolate bar? I'm going to claim, no, it is not. Regardless of how this chocolate bar is arranged, as long as it's a rectangle, Bn is fixed. It just depends on n alone. And okay, so let's give an example. Like, so this is a chocolate bar, and if I want to divide it, let's say I want to take this cut, so that's one cut, and then I have these two pieces, right? So I take one cut to divide this. It's a break number 2, and I need a break here now. So it's a break number 3, and so the number of breaks that were needed to completely divide this particular chocolate bar of size 4 was 3. Okay, this doesn't prove to you that any chocolate bar of size 4 needs 3, but you know what? There's not many chocolate bars of size 4. It's this one, and then there is topologically only one more, for which I don't have a picture, but it is just a line, right? 4 chocolate bars on 4 little squares on a line, and that one is also clear. Well, you have to break each line. How many lines you will have? 3, right? Because it's 1 by 4. I should add that to the side. So that will also be 3. Let's look at this guy, and now you know, just sort of quickly vote. How many lines do you need to subdivide it, right? So okay, just divide it in, you know, anyway, right? You need 5, yes, like here, and 1, 2, 3, 4, 5, right? But also I can go 1, 2, and then I will have to cut 3, 4, 5, because at that point these vertical pieces are separate. Or perhaps I can use kind of a recursive process. I cut here, and this is a bar of size n-2, and this is a bar of size 2. And if I have already shown that the number of cuts that are required to divide this guy is some constant, and so is this one, because these are smaller numbers, then perhaps I can use it to say, okay, how many cuts did I need to cut this guy? That's a kind of recursive thinking, right? That well, we use in algorithms to design recursive algorithms, but also you can see, here in this case, use it to show that these processes have some constant characteristics that are independent of how exactly you perform them. The theorem is that you will only need n-1. It was true here for 4 bar, I needed 3. It was true here for 6 element bar, I needed 5 cuts. And also, if you arrange 6 on a line, then you can clearly see that you need 5 cuts as well, right? There is actually no other way to arrange 6 pieces, right? So let's show that in general, if you have an n chocolate bar, you need n-1 cuts. So let's do the base case, n equal 1, no cuts necessary. In other words, the theorem is true about n equal 1, right? I did it with a 0 cuts. And here is the inductive step. Now suppose that from k 1 on, if for I element chocolate bar, where I is anything between 1 and k, to divide it, you need exactly I-1 cuts. Suppose this predicate was true. Then what I need to argue is that that based on this assumption, if I can show that this formula is true about k plus 1, in other words, the bar with k plus 1 elements requires exactly k, then I would have this proof by strong induction. So let's see if this can be argued. If for any ki in this range, cutting up I element piece of chocolate requires I-1 cuts, then we will try to argue what I just said based on that the k plus 1 element chocolate bar requires k breaks. And now here's the argument. You have a k plus 1 bar. Regardless of how you cut it, you will always end up with 2 pieces that sum to k plus 1. So you will end up with some k1 k1 element bar and k2 element bar, where k2 is k plus 1 minus k1. Now, because this cut was non-empty, right? You actually cut something. So therefore, k1 and k2 must both be at least 1. But if both of them are at least 1, then there is also at most k, right? Because neither of these guys could be k plus 1, because then the other guy would have to be 0. They sum to k plus 1. So they are in this range. So therefore, you can apply this hypothesis to both of them, both to k1 and k2. In other words, the sub-bar, say you have the main bar, it has k plus 1. You created the left sub-bar with k1 element and the right sub-bar with k plus k2 elements. Both of these sub-bars, you can now use the hypothesis about that regardless how you cut the k1 sub-bar, the number of cuts it needs is k1 minus 1, because k1 fits into this range. K2 also fits in this range, so therefore, the number of cuts the right sub-bar requires is k2 minus 1. So how many cuts did you need total? 1 cut to divide into k1 and k2 sub-bars, and now by the induction, by the inductive hypothesis, this many to fully subdivide the left guy, and this many to fully subdivide the right one. So this is the total number of cuts. If you just group them, this k1 plus k2 plus 1 minus 1 minus 1, so minus 1. And k1 plus k2 sums to k plus 1. So this is k plus 1 minus 1 is k, which proves this. And now you'll see, okay, how exactly this matches recursive algorithm, right? You have some task dividing chocolate, is just a mental experiment, doing some processing of some data structure, which you use by a divide and conquer, split into half, and let's use the recursive process for the left and for the right. Now, beautifully, whatever the recursive, something was true about if something is true about this recursive process on the left-hand side and the one on the right, then you can argue that the same must be true about the top one, right? In this case, it was cuts in a chocolate bar. In the algorithm examples at the end of chapter 2.8, in sections towards the end of chapter 8, these will be algorithms: sorting, search in a list, okay, and of course more examples in later classes. Okay, so that's all I wanted to say. I'll take questions if you have. Okay, I have some more examples, but you can see on the slides. I will stop recording, just in case somebody wants to ask questions and feels more comfortable that way.